Hello, good morning everyone. In today's video, I am going to discuss to you on how to get the area of the leaf using integrals. So, things to do. First is prepare your leaf. Second, draw an XY plane on a graphing paper. Third, trace your leaf on a graphing paper. This one. And then the fourth one, locate the endpoints of your leaf. So we have here the endpoints. So this portion, the endpoints is 0 and 9, while on the right portion of your leaf, the points is 24.5 and 9.5. And then the fifth one, draw a broken vertical line on your traced leaf. So we have here a plenty of broken vertical line. So the purpose now, why we have a plenty of broken vertical line, so for us to get the intersecting points. So in the sixth one, locate your intersecting points. So we have here the upper curve intersecting points 0 and 9, 3 and 12.8, 7 and 14.8, 11 and 15, 15 and 14, 19 and 12.2, and then 21 and 10, 23 and then 9.8, then 24.5, 9.5. So the same process, this is the intersecting points of the lower curve. So our main goal here is to get the area of our leaf. So in this portion, we will name, or we'll be using the upper curve down to the horizontal line area as our f of x, while our g of x is the lower curve down to the horizontal line. So for us to get the area, this portion, the area of this leaf, we are going to subtract g of x from our f of x. So for us to get the equation to solve this one using integrals, we have to use these intersecting points, the xy coordinates. We will be using this one as in our interpolation. So in our interpolation, we will be using Excel application. So for now, we will open an Excel application. Okay, here we go. So this is our Excel application. So in the first column are the x coordinates of our upper and the lower curve, while the second column is our y coordinates of the upper curve, and then the third column are the y coordinates of our lower curve. So to get the equation of our lower and upper curve, we have to interpolate these points. So we have to highlight, go to insert, and then chart, choose scatter, then this third figure. So as you have noticed, we have already here the image of our leaf. So to get the equation of our upper curve, we have to click the upper curve and then right click, choose add trend line. And then as you have noticed in the right portion, we have to choose the polynomial and then the degree of 3, and then display equation on chart, display r squared on chart. So as you have noticed, we have here already an equation of our f of x. So our equation is y is equal to 0.0002x cubed minus 0.1109x squared plus 1.5308 5x plus 9.0223. So that is our equation. And then that is the equation of our upper curve down to the horizontal line, the area, the equation. So at this point, we have to get also the equation of our g of x. So we have to click the lower curve, then right click, choose add trend line, and then on the right side, choose polynomial, then degree of 3, display equation on chart, and then display r squared on chart. So we have here our equation on our g of x. So as you have noticed in the equation, we have r squared. So the r squared here meaning the statistical accuracy of our equation. So we have here the statistical accuracy on our f of x equation. It is 98.02%. So this equation will be used in our integral model. So we will come back on our previous presentation. Okay, so the area of the leaf is f of x minus g of x. So the area of the upper curve down to the lower, the horizontal line, and then minus the area of the lower curve down to the horizontal line. So this is our the equation we obtained earlier in our Excel. So we have here the equation of our f of x and then the equation of our g of x. So this time we'll have the integral model. So based on our equation, we have here the integral model of our f of x. We have the integral 0.002x cubed minus 0.1109x squared plus 1.5305x plus 9.0223 dx evaluated from 0 to 24.5. So why 0 to 24.5? Because this is the width of our, this is the measurement or the width of our leaf. So next is we are going to get the antiderivative. So as you have noticed, we have here the denominator. So what is whatever the value of our exponent will be the value of our denominator. So the question now is, why is it that this is from cube and then in our antiderivative it become 4? It is because the rule of our antiderivative is the constant, the exponent must be have an additional of 1, always plus 1. So next is we're going to evaluate. So this is the f of b minus f of a. So our f of b is our upper limit 24.5, while our f of a is our lower limit, which is 0. So using your calculator, you are going to plug in this value. So you will come up the area of the upper curve down to the horizontal line, 316.90 square centimeter. So the question now is, why is it square centimeter? Because we Previously, we used a graphing paper, and then the graphing paper, each length, grid, the length of each grid is 1 centimeter. And then the next thing to do is to get the area of our lower curve down to the horizontal line, which is, we named that one as our g of x. So the integral model of the area of our lower curve down to the horizontal line is the integral of negative 0.0015 x cubed plus 0.0958 x squared minus 1.4167x plus 8.8521 dx from 0 to 24.5. So next is the same process. We have the antiderivative. So whatever the value of our exponent will be our denominator, because the exponent here always have an additional of 1. Next is we have to evaluate f of b minus f of a. So our f of b, the value of our upper limit is 24.5, while the value of our lower limit is 0. So we have to plug in this one in our calculator. So we will obtain the value of 126.19 square centimeter. And then our main goal is to get the area of the leaf, which is f of x minus g of x. So we have here our f of x, the area of our f of x is 316.90 minus our g of x is 126.19. So we come up the area of our leaf 190.71 square centimeter. So that's it. Okay, so I hope you learned something in my discussion today, and God bless everyone.